So it's my pleasure to welcome Monica Nunes, who is a guest scientist at Fermilab. Monica has been associated with Fermilab for the last more than 5-6 years now. And Monica has been working on LArTPC as well as SBND, and she's also a collaborator on Beam. Monica said that she has an interactive slide for her talk, so I'll let her introduce herself. So yeah, Monica, please take it away.
Hi everyone. Avni, thank you for the invitation. I'm very happy to be here today and very nice to meet you all. So yeah, I am gonna talk about the Short-Baseline Near Detector, the construction that is going on. So now this doesn't work.
You need to click on the screen for it to work now.
Oh yeah, nice work. Yeah. So yeah, so I'm Monica Nunes. I'm from Brazil. I did all my studying there. So I did my bachelor, my master's, and my PhD at Unicamp. I was a postdoc at Syracuse. That's when I met Avni too. So I was a postdoc there for 1.5 years. And now I am a guest scientist at Fermilab. I was hired basically to build SBND. I started on SBND in 2019, so it's very recent. It's very recently since I joined. I'm currently one of the installation coordinators, and also I'm a coordinator for the QA/QC that we are doing now. So yeah. So let's start from the beginning. So neutrinos in the standard model. The whole reason why we're building SBND is to study neutrinos. Neutrinos in the standard model, they appear in 3 flavors, as we know. So they are each one associated to one of the charged leptons. They interact via weak force through the Z or the exchange of Z or Ws. And according to the standard model, they are massless, which is very interesting. And then I think this is out of reach. It's right behind the computer. Yeah. But we learned that they can oscillate, meaning that they can change between flavors as they travel. And this can only happen. What? This can only happen because they are not massless. So they have a mass different than 0, which now makes them not like fit exactly perfect inside the standard model anymore. And this could be pointing to physics beyond the standard model that we know. Okay. What?
Would you prefer using the keyboard?
Maybe.
I can slide. I can also.
Oh,
yeah.
Okay. So yeah, the way that neutrino oscillation happens is basically because the neutrino flavors, they are a superposition of well-defined mass states. So there it's a combination, and the way that the defined flavors are related to the defined mass states is through a unitary transformation, which goes by the PMNS matrix. So that's how we can do the relation between the flavor states and the mass states. And the way the neutrino oscillation, the neutrino oscillation happens is because it's like this. So the neutrinos that are produced in the flavor states, they are either produced as a mu neutrino, as an electron neutrino, or a tau neutrino. As they propagate in their mass states, and then when we detect them again, we detect them on their flavor states again, which may or may not be the same one as the beginning. So as they travel here, some change in the flavor could happen. And the way that we know about the flavors on the production and on the detection is through a charge current interaction. Well, look into the lepton that is associated with this interaction, we can ID the neutrino flavor, either in the production and on the detection. And as the neutrino travels, the combination of the mass states, they get out of phase. With one another, and then the sum at the end, after they traveled for a while, may not correspond to the same combination that it was on the beginning. So it may no longer correspond to the same flavor from when it was created. So this is the way that we explain we look into the probability of the oscillation from from the flavor alpha to flavor beta. We just propagate the neutrino. We use the wave plane solutions. And then if we look into a two-neutrino system, which is way easier to deal with, and it's also applicable to what we do, we arrive to this equation that looks into the probability of oscillation. The probability of oscillation is related to the delta m square, which is the difference of the square masses of two mass states, also the mixing angle, and it also depends on the distance that the neutrino traveled and on the energy of the neutrino. The experiments can control this, so we can place our detector with a certain distance from the source, and we can produce our neutrinos with the energy that we need. So we have control over this part here, and that's very interesting because then it allows us to play in different situations. And then in the study of neutrino oscillations, there are many studies that happened, but there were some experiments that found some anomalies. And then these anomalies could be that there is someone else photobombing our oscillation. So we know very well the three flavors of the three neutrino flavors, but could be something else there, and we don't know yet. These anomalies that we found, they go into the low energy problem. Miniboom found some evidence of an electron-like excess from neutrinos from particle accelerators. So Miniboom is a Cherenkov detector. It was on the Booster Neutrino Beam at Fermilab, which is one of our neutrino beams that we have there. So this is the shape of the Miniboom detector. And it saw clear excess on the electron side, the electron part of the neutrino flavor, which was not expected. So this clear excess that appeared in the low energy range was something that caught our attention. And
that excess is seen in your plots.
Yeah, and then it's
low energy bins.
Yeah, it's seen here.
Okay.
The way that these, the way that we know about this is that the problem is that the anomalies, they cannot be described by the three flavors of neutrinos that we know. So nothing that we knew could explain what those results showed. So this could be pointing to physics that is to new physics in the neutrino sector. So if we introduce additional neutrino states with larger mass square differences, this could explain this oscillation happening in these small distances. So the minimal model for this explanation would be a 3+1 neutrino mixing. So these, we just add one more neutrino to the three known flavors. This additional neutrino, since it doesn't interact with anything else, like it doesn't interact with the weak forces, so it's called sterile neutrino. It doesn't interact with anything like that we see outside, but it, I don't know.
Are you kicked out of Zoom?
No, I'm still there.
Excellent.
But what happened here? I don't want to do this now. Where are my slides?
Those are your slides. You just need to go.
No, this is not. This is a different talk. This is the Teflon collaboration call. Your screen sharing is paused. Resume share. Resume share. Resume share.
I see your screen. I see your screen though on my.
If I click, it doesn't change the slides.
If you shared only like a certain window, and then
Yeah, but where's?
Can you stop share and then share again? Yeah.
How did the window close?
I have no idea.
Was it PowerPoint?
No, it was here. So I just opened the presentation again. Let's share. And I was here. Okay. So yeah, the possible explanation would be introducing a new neutrino to this scenario, and this neutrino would be called the sterile neutrino because it doesn't participate in any other weak interaction. This new sterile neutrino would be composed by a heavy neutrino, which the new delta M square would be in this order here between 0.1 and 10 EV squared. And then the mass hierarchy, the way that is we know nowadays would be something like this. So all the other neutrinos, the delta M square is like very low here because they're very it's very small, but this new one is way bigger. Okay, so how do we produce neutrinos? So when we look to neutrinos coming from a particle accelerator, we start like this. We always start with the protons. We accelerate those protons until the energy that we want, that we need. We shoot them into a target. From this target, many mesons, like mostly pions and kaons, they're gonna come out. So charged pions, charged kaons. They are gonna go through a magnetic horn, which can select the charge, which can select the signal that we want. So in this case, we are just selecting the pi plus. We are rejecting the pi minus. The pi's, the pions that are gonna go through decay pipe, and then they're gonna decay into muons and neutrinos. We don't do muons, so they pass by an absorber. The neutrinos, as we know, they can just cross everything, so they are just going to keep going, and this way we have a neutrino beam. So in this situation, like, we cannot aim at beam of neutrino after they are produced, but we can aim when they are still charged particles. So this we can aim to the direction that we want, that we need. And then how do we detect those neutrinos? So a beam of neutrinos is just coming through your detector. It is going to find the target, so it's going to find the protons, the neutrons, the nuclei of your detector, and then many things can come out of these interactions. So we can have more neutrino appearing, we can have pions, we can have muons, we can have electrons, protons, kaons, and so this is what we see in some kind of some particular kind of detectors. That's what I'm going to show now. But yeah, so many things can come out of this interaction. And our idea is that we need to see what's coming out. So we need to learn to read all this information. So how the perfect neutrino detector would be. So we need a large mass to compensate for the small neutrino cross section. So the bigger masses that we have, the higher chances that we have of having interactions happening. We need to be able to identify the neutrino type, but the neutrinos itself, they don't give us any information, like they don't leave any signal in any detector. We need to be able to measure the forward momentum of the incident neutrino, so we need to be able to get this information somehow. And these two things here we can do by looking into the particles that come out of the interaction. So looking to the particles that come out of the interaction, detecting their type and detecting their sign, measuring their energy and the direction, combining all this information from the outgoing particles can give us the information about the incident neutrino. So we need to be able to collect all this information here to reproduce the information of the incoming neutrino. And it's not easy to be perfect. It's a lot of things to do. So to trying to get like close to perfection, we have LArTPCs. So LArTPCs is the short for liquid argon time projection chambers. They're basically digitized versions of our old bubble chambers. So they give us very good imaging and calorimetry information. This is a picture of an old bubble chamber, right? And they allow us to have the 3D reconstruction of the trajectories and the interactions. We can see everything that is, we can see most of the things that are happening there. We use Argon as the neutrino target and also as the detector itself. It is scalable to large volumes. So Argon is fairly cheap to buy, so it's scalable to large volumes, which is which is what we need. So how does a time projection chamber works? So the neutrinos itself, they don't leave any signal inside the detector. We don't see anything. So the neutrino arrives here and well, just nothing. And then they interact. If we're lucky enough, they're going to interact. From this interaction, other particles are going to come out, mostly charged particles. Those charged particles, as they travel inside the detector, they are going to ionize and excite the liquid argon atoms, meaning that electrons and 128 nanometers photons are going to be created. So as the neutrino travel here, many electrons are going to be created on their paths. This whole chamber is feeling an electric field, and with this electric field, is going to push the electrons towards the readout planes. So the photons that appear here, they're very fast, so they can be read like basically immediately. They can be used to trigger the event, the 3-0 of the event. The electrons, they are drifted slower, so they take some time, but then they arrive in some readout plane. And then the readout system for the electrons and the light together is going to give us precise information about the interaction. So in this case here, we have the light collection system right behind the wire plane. So basically, we just created the electrons, we drift them towards the place where we want to read their information, and we collect all the information that we can from the electrons and from the light that is created there. So this is just a small animated version. We have a neutrino coming. We don't see the neutrino information. We don't see anything about the incoming neutrino. And at some point out of nowhere, like many particles appear. So basically the interaction happened there. And as the particles travel, they are gonna excite the liquid argon atoms, and the electrons are gonna be drifted like this. Since it's a uniform electric field, the electrons are gonna be drifted organized. So then we collect all the information and we can really see what happens. So this is what we see from these, from the microboom TPC. So here is the information about time, basically, and this the wire number. So it's like we are looking this information from the top, and these are different views. So as you can see here, we have 3 planes. 2 of those just collect the induction signals. So we have 2 induction signals here, and then we have the last one which collects the electrons itself, and then we can see all this information. So these combining the 3 views that we have, plus combining the time that the particles took to reach the wire planes, we can have 3D images of what really happens inside the TPC, which is amazing. We can understand, we can collect a lot of information of everything that is going on in there. So this is very important, and this is something that we want to explore a lot for neutrino experiments. So we have a few LArTPCs at Fermilab. Some exist and some are still in the dream world. So we have the Short-Baseline Neutrino program at Fermilab, which is going to look into neutrinos propagating on a short distance. And we are planning the future Fermilab long baseline neutrino program with June, which is the neutrinos are going to travel 1,300 kilometers underground from one detector to the other. And then we can study what happens in this case. I'm not going to focus on the long baseline program, but it exists. And a lot of things that we learned from this small program from the short baseline is going to be applied to the June, which is very important for us. So short baseline program, neutrino program at Fermilab is a LArTPC based, a multi-detector LArTPC based sitting in the Booster Neutrino Beams. So basically all that thing that I told you about creating a neutrino beam starts here. We start with the LINAC, protons being accelerated, it goes to a booster ring, and then protons, they reach a target here, and then we have then we have the neutrino beam appearing from here. So then we are going to look if in this trajectory here, passing by 3 detectors, we have oscillations happening or not. But why do we need this? So as I was saying on the beginning, the problem with the low energy excess is it arises from the fact that with Cherenkov detectors, it's very hard. We cannot distinguish electrons from single gammas. And then we cannot determine the composition of the excess. So this was the plot that I showed you before. So this is the excess that we saw, and this is the biggest source of background in these results, and coming from pi-zero misidentification, basically. The way that this happens is because in a Cherenkov detector, this is the signal that we see for each kind of particles. So muons, as they travel, they are going to create concentric rings. So and they're very clear. So you can see very clear signals from muons. Awesome, amazing. And then electrons, as they travel, they're going to create a fuzzy ring. And then we can see here, okay, we know it's a detector. We know it's an electron. It's very different from a muon signal. Okay, amazing. And then pi-zero is going to decay in 2 photons. And then the 2 photons, they are going to propagate, and each one is going to create 1 fuzzy ring. If the 2 photons are together, we can see the 2 fuzzy rings together. So we can clearly differentiate these 3 things here. But what if 1 photon escapes? What if 1 photon takes longer to convert? What if something happens and then we have only a single photon here? Then it's impossible to separate this fuzzy ring from this fuzzy ring, right? This creates a big problem. We don't know how to separate between electrons and photons. And yeah, so then we have this huge background here. And then LArTPCs can help us with this. So the way that the way that LArTPCs helps with this is because we can look into the calorimetric information, we can look into the energy, the position information, and also to the topology of the event. So it's very easy to separate the electron signal, not very easy, but it's doable to separate the electron signal from the photon signal. So this is an example of an electron shower that we call. It's like very fuzzy, very messy. It creates a shower. And this is a shower created by photons, 2 photon showers. The difference is that the start of the shower here is done only by a single charged particle, just by an electron. So if we look at the charge deposited on the beginning of the shower, is a charge of 1 electron or 1 positron, right? But here, the way that the shower of a photon starts is because the photon is going to decay into positron and electrons. So we are going to have 2 charged particles at the beginning of the shower. So the information, the charge information that we see on the beginning of the shower here is going to be double what I expect for electrons. So that's what it shows here. These are showers started by electrons. So it's just like one charged particle. And then if you look at the shower started by photons, it's like double that. So it's very clear to separate them this way. And also, if we look at the topology, the electron shower is connected to the vertex of the interaction. When the photon shower is there, it shows a gap because it takes a while for the photon to convert into electrons and positrons. So it's doable. We can separate this. So LArTPCs can be used to understand better the origin of the excess. So for this, we have the SBN detectors, the short-baseline neutrino detectors. The short-baseline from Fermilab starts with a near detector, or the middle detector, which is microboon, and a far detector. So we have the targets, as I showed you from the Booster Neutrino Beam. We have the protons arriving here. That whole thing that I explained about the horn and the decay pipes happens here. And 100 meters away from the target, we have the first detector, which is SBND. And then as the same beam travels, it's gonna pass through microboon, and then it's gonna travel and it's gonna pass through Icarus. So the 3 detectors are looking to the same neutrino beam, which is very interesting. This is what we expected to see in the oscillation in case there was a sterile neutrino, in case they were using the 3+1 model. So this is what we expect to see, the neutrinos on SBND with almost no oscillation, and the peak of oscillation here on the far detector. Microboon, as you know, microboon was operating since 2015. It stopped it last year, right? Was it last year?
Yes.
Yeah, 2021. Yeah, and then microboon was a TPC that was built to look into the origin of this excess. Microboon was sitting like right beside the previous mini boon detector. So it was basically the same distance, the same baseline, and it was looking to the same beam. So it should see the same thing, right? But Microboon didn't see an excess on the lower energy range, which is very disappointing maybe for some people, but this does not rule out the existence of the external neutrino. So to enter the next phase, to keep exploring the existence of the external neutrinos, we need to do oscillation search, which requires an increased exposure to a larger far detector, which is okay. We have Icarus now, which is big. I'm not going to focus on Icarus now, but there is a far detector, so we are taking care of this. And we also need a near detector for systematic constraints. Okay, so that's the point of this talk. So we are going to talk about the near detector that is being built, and it's called SBND. So SBND, a short-baseline near detector, is going to be 112-ton active volume LArTPC. It's sitting 110 meters from the BNB neutrino source. It's this beautiful thing here. So this outer vessel here is the cryostat, and this is the TPC, which is hanging from the ceiling. This is amazing. I love this idea. So the whole detector is hanging from the ceiling. The SBND is going to see over 1 million neutrino interactions per year, which is amazing. It is a very large data sample that will allow us to do a study of neutrino-argon interactions, cross-section measurements with an unprecedented precision. This is very good. And it will also give us very high statistics measurements of the unoscillated BNB. And this is critical for neutrino oscillation studies on the SBN program. So having the constraints on the near detector is going to be very important for us to keep this search for stellar neutrino and even new physics and a lot of things that can happen there. Okay, so SBND is a brand new detector. We are building it from scratch. It started out of zero. These are the parts of the SBND. This is the original concept, the original drawing. We have a cathode in the middle that is going to provide minus 100 kilovolts. And it's dividing the detector in two parts. So we basically have two TPCs. So the cathode in the middle and the anodes are on each side. So there are wire planes on this side, on this wall. So we have two wire planes. We have a field cage, which I'm going to talk a little bit more about, surrounding the whole TPC. And then there is a photon detection system sitting behind the APAs, the anodes looking inside of the TPC. So it's a big detector, 4 meters, 5 meters. So this is the beam direction, 4 meters tall. So each TPC has a drift region of 2 meters. It's big. And yeah, so this was just the concept, I don't know, 2000 and a long time ago. And this is SBND now. So we cannot see much, right? So there's a big tent, is like messy. So this is the place where we are building SBND. So let's start with parts that are inside the tent. So we have the ATF. ATF stands for Assembly and Transport Frame. This is a structure that's not part of the TPC, right? This is a structure that was designed to host the TPC assembly inside and to provide all the support for the spoiler alert for the transportation to the near detector building. So we are building the detector in one place and we need to move it to the final destination. So this is the ATF that I'm talking about. This is a white structure. The whole TPC is being built inside it. So we are putting all the parts inside of this ATF. This ATF, this was my first interaction with SBND. I joined SBND this day. It was a load test. So they brought the ATF outside. They put on the load, I think it was 125% of the load or 150%, I forgot now. Some value of the load that we above the load that we expect from the TPC to see if the structure was capable of handling it, but it was. So this was just a load test, and we lifted, we played with the frame a bit. This was January 2020. What, almost 3 years ago. It was very empty. And then to start the construction of the TPC, we had to do some preparation before. So we had to build cling tents around the ATF. So we have 2 layers of cling tents here to provide a clean environment, as clean as it's possibly to have, for the construction of the TPC inside, and also to protect the light sensitive components. We have some components that are light sensitive, so we need to protect them, especially from blue light and UV light. So we have an inner tent that is just sitting around the ATF, which has UV filter sheets. And we have an outer tent, which is this yellow one here, which is movable, which we can like move away from the ATF if we need. And this yellow plastic has UV and blue filters. So this way, the light sensitive components inside are protected. And these attachments here, like Velcro and magnetic tape, so we can still access easily inside those tents. So let's start with parts of SBND. So this is the CPA, this silver structure here, this metal structure. It is going to hold minus 100 kilovolts, as I said. So this is the very middle of our TPC. So we call it cathode plane assembly. We call it CPA. It's going to provide a high voltage, and there are panels sitting in between those windows here. They have reflective foils, and they are covered with TPB to help the light collection system. I'm going to go back to this in a second. So these are the panels as we were installing them, and the TPB, which is a wavelength shifter, is light sensitive. It degrades with time, with light exposure. So as we were installing, we were covering it with black plastic just to try to minimize also the exposure to light, but everything was happening inside the cling tent. And so we have the CPA. Then we have APAs, which are the anode plane assembly, which are the beautiful part. This is my favorite part of the detector. So on SBND, we have, it's going to read the charge information. And on SBND, we have 3 wire planes with wires sitting 3 millimeters apart. So so this is the whole thing. And there's a zoom, so you can see all the 3 layers of wires here. So these 2 planes, so this is a single APA plane, but like the two parts were built in different places. 2 of them were built here at Yale by the Syracuse team. Thanks, Avine, there was a big part of this, and I just saw the place where it was built. It was very, I don't know, I was excited. And then so 2 of them came from here, Yale, and then 2 of them came from the UK, Manchester. So when they arrived, we had to combine them together. We had to couple them together because they need to work as a single plane. So we need to do all the mechanical and electrical connections. And then we need to run checks, of course, to run tests to check that nothing was damaged, and to check that when we coupled them together, they were working. So these were like the steps that we took. So before coupling the 2 APAs, we also ran tests on them, which is we are just like reproducing the test that they did, the Avini and the group, they did it here when they were producing. So we measured the continuity test to make sure that no wires were damaged, were broken, or whatever. We made the isolation measurements. So we put some high voltage in some wire and measured what happened to the neighbor wire to make sure that none of the wires were touching or anything. We did tension measurements to make sure they have the tension, because those wires, they need to be in a certain, they have to hold a certain tension measurement. So this is the tension measurement. We just like shoot a laser, vibrate the wire and see the response. And this is what we were looking at, and these more tests being made. Then once the APAs passed the first tests, they were mechanically coupled together. So we had the metrology crew from Fermilab with us. So we were working together with them, so we could position the 2 APAs right to the right position. We then will lock them in place with the alignment bar. So these two APAs that were sitting in alignment tables, which gave us freedom to go up and down, left and right, and all the directions. And then with the metrologist team, we position them right. We lock them in place with those bars. So there's a bar here. There is a bar on the other side of the APA. And then we also surveyed the position of the APA that is going to be used in the geometry information for analysis later. So it was a very fun time. And then we had to couple the APAs together electrically because these two planes, they came separated, as I told. Sorry for this very bad drawing. I don't have very good abilities. And then we had to couple them electrically so the wires that started here could behave as the same wires as they crossed to the other side. So we had to use jumpers underneath the connections, which was very fun to do, of course. You can imagine how easy it was. And then we managed to spot like broken connectors, which we managed to fix. And of course it happens, but that's why it's important to run tests, lots of tests, so we can monitor if we're doing the right thing or not. So these are the jumpers. These are two collaborators working on making them together. And then we run, of course, more tests. So this is a big part of construction, of detector construction. We need to monitor every step that we take and record all the information so we can do the right thing, right? So we measured wire-to-wire isolation. We make sure that to measure the resistance between all the wires, they were all good. We checked it for the bias. So an SBND with the 3 layers of wires, we are going to have two of them are going to be biased, meaning that we are going to apply voltage to the outermost planes. The middle plane is not going to be biased. There's not going to receive any voltage. So we bias the outermost plane and check to see if all the wires were receiving were being biased, and they were. So this was very good. We checked plane-to-plane isolation. We don't want these planes to communicate between themselves, right? We want them to behave individually. So we biased the outermost planes and checked the other wires in the middle to see if they were not biased, and they were not. And then we did a very careful visual inspection. Everything looked good. And then we took many pictures to have things to compare, right? And then APAs were ready. We coupled them together mechanically and electrically, and then they passed all the tests that we ran. And then it was time for installation. This was very exciting. But first we need to cover them, of course, because these wires, they're very delicate. We don't want to hear like ding, 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 ding noises. So we covered them with the covers, and then it's time to install it. Let's see. Hopefully this thing is gonna. So this was a whole day process. So the whole APA, the 2 APAs that were inside this tent, which was the same tent that Microboon was built. Everything is happening there, blah, 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 a lot of conversation. And then we are bringing the APA out with the gantry crane. We lowered it on some cribbing. We were doing all the checks. This goes away. Now we are connecting some cards here to help us moving the APA from horizontal to vertical position. A lot of conversation, checks, and to make sure everything was all right. And then we are going to connect the support beam to the APA. We're going to lift it, lift, pictures, put it in, installed. I am here on the top of this lift, installed, placed, made it, and then close everything, of course. So yeah, this was the installation of the second APA. Of course, this took like 1 minute, but in reality, it took the whole day. It was a very interesting day. And as you saw, like we connected the support beam to hold the whole APA. So that's how the detector is going to be hanging from the ceiling. The whole weight of the detector is going to be hanging on the support beams. So we have one support beam for each APA and one support beam for the cathode in the middle. And that's all. That's all the connection that we're going to have. No, I don't see it again. No, move on. Okay. So APAs were installed. So the CPA was already there, as you saw, and then we installed the APAs on its side, which is, I like this view a lot because it relates directly to this picture. So we have the cathode here in the middle, and then the 3 wires here on the right side being measured. So what is happening here is what is going to happen here in real life. So the neutrinos are going to come in, interact, and the electrons are going to be drifted towards these wire planes. And then field cage. Field cage is what goes around the whole TPC. So the function of the field cage is to have, they have like a resistor chain to provide the voltage drop from the CPA to the APA. Remember, this guy here is a minus 100 kilovolts. This here is almost grounded. So we need to have a uniform electric field inside, and this field cage is going to help us with that. This was built here in Yale too, thanks to Domenico. Angela was also involved, and Giacomo. This was a lot of work. I'm sure it was built a long time ago, and it was installed recently. So yeah, this was a picture when we were installing. And this is the process of installation. This is Angela underneath. So we started installing the bottom field cage layers. So this is the CPA here in the middle. We had the panels on top. We just left the middle, the lower row without the panels, so we could have access. So installed the bottom modules. Then it was time to go to the top and to the side. So first we did a mock installation. This is a mock panel. We did a mock installation. This is Giacomo laying on this scaffold, helping with this. And then it was time to the real installation. This was the first one that we installed. It took like what, 10 hours. It was a very long day of installation. It was very scary, but it worked out. So we were installing this first module here, and then we installed the top ones, and then we went to the top side ones. So on purpose, we left the bottom sides open. So these were left open because we still needed to have access to inside the TPC. So we still need to do stuff inside the detector. We still need to connect all the field cage modules to the CPA. So the connection goes from inside here. And we need to remove the plastic, the black plastic covers of the CPA. We had to install optical fibers to help with their part of the calibration for the photon detection system. So everything had to be done here, like right before. We had to delay this process as much as possible because this TPB here is light sensitive, right? So we had to delay the exposition of these things here as much as possible. So this happened very late, and we were able to access we were able to access the TPC using this boom lift, which was very fun. I drove it. I didn't hit anything, which nailed it. Amazing. And this is a very interesting view, which is from inside the TPC. While I was there, I took this video that doesn't want to play. Really? Why?
Is this a video on YouTube?
No, it is from my phone. Go back. Let's see if it plays now. Yeah, so this is a very interesting view from inside. This is what the neutrinos are going to see. It was very, I don't know, magical to be inside the TPC. Like this is the last TPC that we are going to be able to see like in real life, because Dune is going to be built underground, most of it, and it was very cool to see the TPC appearing and building the whole thing in front of us and having access to inside it. Yeah, it was very interesting. So yeah, this is the inside of one TPC, of course. And then after we did everything that we need to, no, not again. Then we closed the field cage. So then Giacomo, Domenico, Giacomo didn't come. Domenico and Angela, they went there, and then we closed the bottom modules. And now we have a closed TPC. So this happened in June this year. We were very happy. The TPC was closed, was very close to an end. More parts that we have, like we have cold electronics. So the cold electronics, they are installed, as you can see, they are covered. So this was a while ago. So we covered them, of course, to protect all the boards and all the connections. And here the idea is that the signal is pre-amplified and digitized in code to reduce noise, which helps a lot. Like Microboon had warm electronics. Icarus, I think it also has warm electronics. So yeah, this is very helpful. What else we have? We have a photon detection system, which is a modular system that sits behind the APAs, behind the wires, looking into the TPC. So the way that we have this is that we have those boxes. We have 24 photon detection modules, boxes, and each box has 5 PMTs. So those big round things here, we have 5 PMTs, these kind of PMTs. And then in total, we have 120 PMTs on the detector. We also have 8x Arapucas per module. So Arapucas are a design that was it was developed in Brazil by a group from my former university. And the idea is to trap light inside. So we have big-ish windows here, but we have 2 silicon PMs only inside. So the idea is that the light is going to go in, it's going to get trapped inside the Arapucas, and then they are going to bounce around until they reach a silicon PM to be digitized. So yeah, this is the whole thing. And the interesting thing is that we have coated PMTs, because again, so yeah, I'll go back this. And then there's the installation here happening. It was also fun to lift all the boxes and put them in place. So the idea is that some of the PMTs, they're coated, some of them are uncoated, meaning that the PMTs, they see visible light, they detect visible light. The scintillation light that is going to appear inside the TPC is 128 nanometers. So it's VUV part of the spectrum. So you need to convert it from 128 nanometers to the visible range. The way to do this is to raise a wavelength shifter. So some of the wavelength shifter is placed on the PMTs itself. So the coated PMTs, the white PMTs, the white circles, they are coated, meaning that there is a layer of wavelength shifter right in front of the window. So as the photons they pass, they convert, and then they can be read by the PMTs. Some are uncoated. So how do we do this? So this is how it happens inside the PC. We have the scintillation happening here. Light goes in all the directions, right? Some of them are going to go straight to the PDS system, and are going to pass through the wavelength shifter here, and then it's going to be detected by the PMTs. Some of them are going to go towards the cathode, to the opposite side. There's no light collection system here, but there is a cathode with reflective foils. They're covered with wavelength shifter. So the reflective foils covered with wavelength shifter is going to make the photons to reflect on a different energy, the different part of the spectrum. So it's going to be visible now. And then this reflected light can be detected by the uncoated PMTs, because now they can see this, right? So this way, and also the Arapucas. Some of the Arapucas, they have they are sensitive to UV light. Some of them are sensitive to visible light. The whole point is we can detect the light that goes to all the directions. We can detect five-ish. Okay. We can detect the lights that go. We can detect the light that comes directly from the scintillation, and also the light that is reflected. And this gives us a very an excellent high uniform light collection for the whole detector, and very good timing resolution. So this is SBND now. We have a closed and complete TPC. So this is a view from inside the field cage modules. This is pointing the camera towards the wire planes. You can see the cool reflection here from the wires. This is the view from the cathode. We can see the beautiful cathode with the reflective foils panels there. And this is a picture from between the modules. I love this view because you can see the whole TPC. This is the cathode in the middle, basically common for both sides. And then you can see the drift distance here very well. So yeah, we have a complete TPC now, and it was complete last September. So we had, of course, many years of people working, many people involved. We had, of course, COVID, we had delays, but it all worked out somehow. And at this moment, the only thing that is missing is that we are finalizing the cable routing, doing more QA/QC tests, because this never stops. Then we are going to cover the whole ATF in protective plastic. And after everything is done, we are going to reconfigure the whole ATF for transportation mode. So as I said, was a big spoiler at the beginning. We need to move the detector to its final destination. So this is the place where we are building the detector, the D0 assembly building. And then this is the place where the detector is going to live forever. So we need to find a way to go from here to here. So this is the near detector building. It's a very beautiful building that's going to host the detector. In parallel with the TPC assembly, we were building a cryostat. So we have now a cryostat that is going to be used for the TPC. It's the same kind of brain cryostat that is planned to be used for Dune in the future. And yeah, so we basically were building both at the same time, the cryostat and the TPC. So now we have the cryostat complete. This is the cryostat cover, and we are working on the fine details to have the cryostat ready to host the TPC. But we have just a small problem, and it's a very small problem. This is the door of the building where we are building SBND. This is the ATF. The ATF needs to go through that door. And this is how much clearance we have. This is how much clearance we have. It's very scary, but it works because we did several tests of taking the ATF out of the building to load tests, as I showed on the beginning. But yes, it is very scary. And now we have a TPC inside it, right? Okay. But it fits, and we are doing a good job. We're going to do a good job pushing it out, of course. So after the ATF is outside, after we push it outside from the door, a crane is going to pick it up with a lift, it's going to swing, and here we are going to have a trailer waiting for the ATF, and we are going to place the ATF on top of a trailer. We are going to secure the ATF to the trailer, and then we are going to start a road trip. So SBND on tour, as we call, this is the possible map for the trip. We have two options. There is this route and there is this route. They both have their advantages and disadvantages. So to test, to try to see which one is the best, we performed test runs. So we did test runs with an empty trailer and also with loaded trailer. So we put the same weight from the TPC on the trailer, and we tried to mimic the height of the center of gravity. We loaded the trailer with inclinometers and accelerometers to monitor the routes. So these are some pictures from the test runs that we did. So this was on an empty trailer. This picture is from this building from the top. So people are very confused with this thing, because we were stopping the traffic, of course, it was a mess. And people are like, why are you doing this? It's an empty trailer. No, there were 2 water bottles here on the back. So yeah, people are very confused, but yeah, we did it. And then we put the load on, and this was performed just last Tuesday. It was very interesting. So this is from one route, this is from the other route. Once the detector arrives to the near detector building, we are gonna get the same crane to do the inverse process, like unload the ATF from the trailer. Then we are going to move inside of the building. This is the space that is going to take in the near detector building. This is the door. Here is the cryostat in this hole. So the TPC is going to sit here on the outside for a while so we can perform more QA/QC tests and the road to data. So the move is expected to happen now, basically, November, December this year. It's very close. Then after we move the detector, we are going to do a lot more of QA/QC. We are going to do cable routing, cable connection, attach the top of the cryostats to the top of the TPC. Then we are going to move everything to inside the detector, probably around spring 2023. Then we are going to do more QA/QC, more cabling, more instrumentation installation too. Then we're going to slow it down. This process takes a very long time, and we expect to be ready for cryogenic operations in summer 2023. So this brings me to my summary. And the SBN program at Fermilab has extraordinary neutrino oscillation search. It's going to search for extraordinary neutrinos, oscillations, new physics, and it's going to do technology developments. Building SBND is going to give us valuable experience for building Dune. We have now complete detectors since last month. We have detailed QA/QC procedures for all the future steps of all the subsystems. SBND construction went great. And this only happened because of an amazing team of students, postdocs, scientists, the techs, and the engineers that worked like during these COVID times that we know it was not easy, but we were all doing our best and it worked out. So exciting times are ahead. Stay tuned because SBND is gonna start taking data soon. And this is the collaboration. So thank you.
Thank you, Monica. I have time for a couple of quick questions. First from the audience here.
I have a quick one. What's the advantage of having basically like this big divided into two
Two TPCs instead of one. So that one of the advantages is that we need the electrons, they need to be able to drift from where they were created to the wire planes. The more that they need to travel, the more chances they have to get like trapped into other atoms. So we need to minimize this. So we want a big detector, but we also want to reduce the space that electrons need to travel. So dividing it by 2 helps with this. So yeah, it is also important because argon, sometimes we have impurities that are going to trap the electrons, and yeah, there are many things that could happen to trap the electrons on the way. So reducing it is an advantage for us. We can collect more, we can have more information, charge information.
One more question.
Why do you use both PMTs and separations for your light bulb?
Very good. So PMTs is because we know them very well, right? So they are not great in many senses, but we know how they work. So this is amazing. And the Arapucas, we don't know yet how 100% how they behave. So it's basically, this is going to be a very good part to understand more about the Arapucas. So comparing whatever we get from the Arapucas to whatever we get from the PMTs, we can understand them better. So that's why. So running only with Arapucas would be tricky because then we would be lost. We didn't know how to compare the data, right? And having the PMTs there, it's easier to do this.
So it's sort of like kind of trying to transition from PMTs.
Yeah, also, yeah.
Okay.
And then this way we could have like a big coverage of the plane.
Yeah.
Any questions on Zoom? I guess not. I have one quick question. How does the data that you accumulate for SBND, how is it going to compare with, for example, the detectors earlier, for example, for microboom, since SBND is located so close to the source?
I saw this number recently. I think what we are going to collect, I think we are going to have the same amount of data that microboom had on all the 5-7 years run. We're going to have it on the first year.
Okay, that's impressive.
Something like that. But yeah, I forgot the exactly comparison, but yeah, we are going to have years of difference, like, yeah, in a short period of time. Or is it a month?
I'm not sure.
Now I am.
I think
Yeah.
it's a month.
Yeah, now, yeah, I think it's a month, yeah. Which is even more impressive, yeah. It's amazing. We're going to have like what is the number? I think 5 million events, like 5,000 events per day, something like that. It's like an unimaginable number for neutrino experiments, yeah.
So let's thank our speaker again for the next slide.
Thank you.